we'll start with number 3 here, and move from there. This one will going to be helpful when you do your olive loaf problem, if you haven't already done it. Because remember, anytime you have a hole, I consider, they call it subtraction, I call it just adding a negative mass. So for this one, we have this circular plate, and we have a hole cut in it, and the hole center is slightly off on the x-axis from the center of the plate, and that's why they only ask us to find it in the x direction, because in the y direction, it's not going to move. It's still going to be in the center of the plate in the y dimension. That's why they only ask us in x. If it wasn't, then you'd have to figure out how it shifted in both x and y. All right. They want the position of center mass of the plate on the x-axis. Assume C is the origin, and the coordinate of C prime is on the x-axis. All right. So here we go. So I have my picture up there. So I'm going to do that the center mass in the x direction, if I do the mass total, then that equals mass 1 x1 plus mass 2 x2. I only have 2 elements here. I've got the plate and I've got the hole. I'm going to assume that is a noisy hallway. I'm going to assume that this has a uniform density. I think it said that. So the mass of this, the mass of the total plate is going to be its density times its volume. And the volume would be, let's see, pi r squared times the thickness, which we'll call T. Right? Rho pi r squared T. And in this case, so the mass of this total plate is rho pi times 4r squared T. Right? Mass is always density times volume. From the fact that my plate has a radius of 2 big R. Okay. Because I'm taking the area of the circle and then assuming it's a regular cylinder. So that's how I get that volume. So that's the mass of the plate. It'd be good to do the mass of the hole also. The mass of the hole is going to be negative rho, and then it has a radius r, so just pi capital R squared T. So its mass is actually going to be 1/4 the mass of the plate. All right. I can use any point as my point of reference. I would recommend in this case using something on the x-axis. And in fact, I'm going to use the origin or where point C is as my point of reference when doing this this object. And then my x will be where the center mass is located. So the way that I do this is my mass total is the mass of my plate plus the mass of the hole, which remember is negative xcm, and then this will be the mass of the plate, the location of the plate center of mass, plus the mass of the hole, which remember will be negative, and the location of the center of mass of the hole. Both the plate and the hole are regular spheres, regular cylinders, so their center of mass is in their geometric center. So for the plate, it's at point C. For the hole, that's at point C prime. but they're regular solids, so they're in their geometric center. So I'm going to have XCM equals the mass of my plate, which is, I'm just going to write more conventionally, 4 rho pi r squared t times 0, because that's the location of its center of mass, plus negative rho pi r squared t times, and I'm going to run out of room here. Whoops. I want to grab that. I want to grab this. Move it over just slightly. And then this is the number that's different for each person. For me, it's 0.74R. So 0.74R. I'm choosing that direction to be positive. That's all over my 4 rho pi r squared t plus my negative rho pi r squared t.
That 0.8R, that's C prime, or that's the distance from C to C prime. Okay.
My 0.74? Yeah.
Sorry, that could.
You said 0.8, but maybe yours is 0.8. Yours is 0.8. And now I solve it. My t's cancel out. My r's, I end up with 1 r up top. You know, so I'm assuming you guys are good with the math after this, right?
Yeah, that whole term becomes 0, right?
The whole first term.
Yeah.
Yeah. That's going to give me a negative, which is indicating that it's shifting, which makes sense because there's more mass on the negative side, right? So I'm going to get a negative answer, which makes sense. So you see what you get, I'll see what I get. We'll meet in the middle. Or let me know if you don't get it correctly. I'll double check my work. All right, so we're going to do number 1, which is another algebra-based center of mass problem. And I think I'll keep mine in terms of L0 until the very end, and then I can plug it in. So, first thing I like to do is make sure that I have all of my measurements correct. So I'm going to go through the mass, and the mass of, I'm going to call this cube 1, this cube 2, and this cube 3. So the mass of cube 1 is rho L cubed. The mass of 2 is rho 8L cubed. The mass of 3 is rho 27L cubed. Those are my individual masses. And then the locations, like the center of mass of cube 1 is at L over 2. For cube 2, we're at 2L. And for cube 3, we're at 4.5L.
Those are your X values, right?
Those are my X values. So my total mass here also will be, let's see, rho times 36 L cubed, right? So I'm doing mass total XCM equals mass 1 X1 plus mass 2 X2 plus mass 3 X3. So my XCM in this case is going to be rho L cubed times half L plus rho 8L cubed times L cubed times 4.5 L all over rho 36 L cubed. And then just solve. Hence why we keep doing problems. Because the best two tools for that is familiarity with the concepts and practice. 4.5. You could also put it down as 9 halves. That is the location of the center of mass of the individual objects. Because remember, the center of mass is the average location of the masses. So, lots of things cancel out here. I'll check mine, you check yours, see if we can beat Eddie and get an answer before him. Right off the bat on number 5. What can symmetry help you with? X and Y are equal to 0 due to their symmetry. You also notice that they kind of gave it away in the problem. Yeah. There's no H next to those. All right, so what's our first suggestion here?
Just setting up the basic.
Yeah. What's the basic equation?
DCX is equal to 1 over n times the integral of d.
Yep. Nope. Yep. Well, now, quite frankly, this not being on the equation sheet, what does that tell you? Either, well, it tells you one of two things. Either they're assuming that you remember this, or they're not going to give you this type of problem on the test. Or that if they do, they'll give you that relationship. All right? Most likely, they're not going to give you this type of problem on the test. But when we get to fields, this practice of being able to do these type is going to become very important. So if you look on the equation sheet, there are equations like this that deal with fields. And when we talk about rotational inertia next week, these will help you with rotational inertia. All right? But the likelihood of them saying, hey, you've got this, find the center of mass, is pretty low. All right? All right, so now we have to make a decision like we've done 2 of these. With dealing with that mass of the cone, are we going to deal with that the mass is the summation of all of the little masses, or are we going to deal with it like we did on one other one and say, hey, I know the formula for the mass of a cone. So you guys think about it, and let's make a decision of which way we want to do it. Rho will cancel itself out. But we can do it. Remember yesterday we approached that one with that the mass is the integral of the individual masses of dm. That's where we approached it yesterday. The day before, we approached it as, oh, I know the volume of this multiplied by rho will give me the mass of it. That was with the pyramid. Well, I did it separately that way with the pyramid. Pyramid, we had it down in both ways. And Megan and I did them after school and they came out. So which way are we doing this?
I would say volume times rho.
Okay. Yeah. So the mass of this is going to be rho times its volume, and its volume is 1/3 pi r squared h, right? And in this case, that r should be large. 1/3 pi capital R squared, and the height of this one is h, so we can leave that in h. So that's our mass. So we can rewrite this now as 3 over pi big R squared times h, integral of z dm, right? But now we need to, we need to get dm in terms of z, because we're looking at where on the z-axis is. We don't want to get rid of the z, but we want to get rid of the dm. So what's our next step? Cool. But our shape isn't a cone now. It's a disc, right? So what's the volume of a disc? Pi r squared h. So we can write the same thing. Leave the z. And we're saying that dm equals rho dv. So in here we have rho. The volume is going to be pi little r squared dz. Little r is the radius of our disk. That's the thickness of our disk. So it's the surface area times the thickness of the volume. Say again? Because I know a cylinder is its surface, its area, cross-sectional area is how I think of it. The surface area times the height. And the surface area, and it's a sphere. It's a circular disc. Circular disc. Circular cylinder has our cross-section that we're moving up and down the z-axis. It does. And now we need, so little r, so that's always a good inventory to do. What in here are variables, and so thus are going to be affected by the integration, and what are constants are not going to be affected. Variables in here, I dropped the pi, I dropped the rho from here. I did that yesterday. The rho and the pi we could pull out. I'm tempted to pull out the rho. Yeah, I'm tempted to pull both of those out. Z is a variable. Little r is a variable. dz says that, hey, keep the z, at least. And that makes sense. So we need to find how is little r related to z. You have that?
Yeah.
How's little r related to z?
Big R over h times in parentheses h minus h.
Say it again.
So negative big R over h times in parentheses h minus h.
And that equals little r?
Yeah.
Little r.
Yeah. Well.
Yeah. I had a little bit different ratio. I had that for a cone, r is to z because they feed. So I can say that R is big R over H times Z. Now this may come out to the exact same thing. Let's see. If we were to distribute that, we would get, I think it's worth doing. We would get negative R, right? Minus Z big R over H equals little r. Close, very close, but I think I think.
Negative big R over, I don't know.
Did you use a triangle and use Pythagoras? Yeah. I think there's just a slight flipping here. Okay. So I'm gonna erase it just so that if people are following along at home. So this is the relationship that I'm going to use. Because it's a cone, it goes up proportionally, right? Okay. So that's going to change this. Remember, we're going to cancel out our rho and our pi, right? So we have 3 big R squared H, the integral of Z times big R over H Z. That quantity is squared dz. So one more rearrangement before I dive into my calculus. I'm going to have 3 R squared H out here times R over H squared. Those are all constants. In here, I've got Z cubed dz. Right? And we're going to do this from 0 to H. We do have bounds. Right? Because 0 is the bottom, H would be the top. So I'm going to pause for a minute to let you guys practice by doing that integration real quick. And then I'll go through it, but I'd like to give you a shot at doing it before I do it. No. Because it's R over H times Z. You got the answer?
I got it.
What is that from that movie? Just keep singing, just keep singing, just keep singing. gonna have to do this quick and then save the video because I gotta do video with my next class. But here's the diagram of it. All right. So we're looking at these little arc lengths here, right? Which would have a mass dm. They're located. The location of them would be for in x and y. For the x would be r cosine theta, and the y would be r sine theta. All right. Symmetry tells us we don't have to worry about the x, right? It's in the center. But there is actually if this was a solid, we could look up where it is on this half circle. But since it's not, we have to realize things like, well, the dm here will be m pi r dl, where L is the width of that piece. All right? Yes? This length here, maybe I should use a different color. Maybe that would help. That red is dl. Okay, and so we take the total mass of this divided by its arc length, pi over r, and that tells us the individual pieces. That's kind of its density, mass over length. That's its linear density, right? Rather than volumetric density. Yeah? Okay. So this is just like we've written before, where dm equals rho dv. Here, because it's a line, it's rho, or not rho, I'm trying to think of the symbol for linear density. It's out of my head. Huh? It is lambda. Thank you. I know. I was thinking J. Because it's a line. And then, of course, we can also use in here the fact that dl is the arc length. So we know that dl is r d theta. Yes? Arc length? Pretty good. So dm ends up being m over pi r d theta, right? Our r's cancel, right? And then, so now we're going to go ycm equals 1 over m integral of y dm. So ycm equals 1 over m integral. Now y, we're gonna put in r r sine theta. For dm, we're gonna put in our m over pi times d theta. And our r is a constant here, right? And our m is a constant, and our pi is a constant. And I've got to pause the video so I can save it. And I'll upload this for those that aren't here